Good morning, everyone. So welcome to my YouTube channel, Math Subject. So today we are going to see fourth lecture on group automorphism. Okay. So let's start today's lecture now. So today we will see that collection of all the automorphism of a group forms a group with respect to compositions of functions. So this is theorem. The set of all automorphism of a group forms a group with respect to the operation of or you can say with respect to compositions of functions. With respect to composition of functions. Okay. So proof. So we write AC is equal to F such that F is an automorphism of G. So G is group here, and I'm writing AG is equal to F such that F is an automorphism of G. Okay. So what is the composition here? So what is the operation here? It is composite of functions. Okay. So what is this? So what is the operation? Let F and G are two functions belongs to AG. The operation FG is operation means there is an operation between F and G. That is nothing but F compose G. Composition of two mappings. How it defined? So F compose G. You are taking A element, that will be F compose A is equal to, you are taking GA for all A belongs to G. So in this way, this operation is defined. Okay. Now we have to show that AG is a group with respect to this operation. So which property will check? Closure property. It is closed under this operation. So that is called closure property. Second one is associative property. Third one is existence of identity. Fourth one is existence of inverse. So first property is closure property. Okay. Let F and G belongs to AG. Okay. AG. Okay. Okay. So what is FG? FG. So let so we know that automorphism is 1 1 on 2. So F G to G is 1 1 and on 2, and G from capital G to G is also 1 1 on 2. So their composition, this implies F compose G from G to G is also 1 1 and on 2. So this implies FG from G to G is 1 1 and on 2. But showing that FG is 1 1 on 2 is not sufficient. You have to show that FG is also a homomorphism. Then it will become automorphic, and this will belong to capital AG. Okay. Now that, so FG is homomorphism. Let A and B belongs to G. Then what we have? We have FG AB is equal to FG AB. Okay. But G is automorphism, so it is homomorphism. I can write it GA, GB because G is a small g, homomorphism. Again, this element GA and GB belongs to group, and I can use property of homomorphism here. So what will be this? This will be FGA and FGB. Okay. So finally, how I can write this? This is what? This is FGA. This is FGB. So this implies FG is a homomorphism. Okay. So what we have actually, since FG from G to G is homomorphism, and it is 1 1 and on 2, we get FG belongs to AG. F and G belongs to AG implies करता है FG belongs to AG. This implies closure property in AG is satisfied. Okay. So closure property is satisfied. Now what is associative property here? Now associative property. associativity, you can say. We know that we know composition of function is associative. Therefore, associative property holds in NG. You take any three function, you take composition of any first two, then with another one, it is equivalent to you take later two and then first one. So associative property with respect to composition operation always holds. So that is direct result of. Now, existence of identity. Existence of identity. Now you consider the identity map. Consider identity map I G to G. Okay. Then what is the meaning of identity map? It maps same element to same element. It means it will map A to A for all A belongs to G. Okay. So therefore I A B is equal to A B. That is I A I B. Okay. So this implies I is homomorphism. Homomorphism. I is homomorphism. Okay. And you can check because I goes to A. This is 1, 1 and on 2 also. 1, 1 and on 2. So identity map is always a automorphism. So this implies I belongs to I. Now for any, you take any F belongs to, take F belongs to AG, or you let F belongs to AG. F belongs to AG, then F I A is equal to F I A. That is I is A. Okay. But I can write this as I F A, because F A is also element of G. It will map to F A. Okay. So what we have? We have I F. So I can write like that. For all A belongs to G. Okay. So this implies this is equal to, this implies F I is equal to F I F. So this implies I is the identity element in G. I is identity element in AC. Okay. Now we are going to prove existence of inverse. Existence of inverse. Okay. Existence of inverse. Every element in AG has inverse in AC. How we will prove it? So let F belongs to AG. So F G to G is 1 1 and on to. So inverse map will be, so this implies inverse map will exist. When inverse map exists, when you have a function that is 1 1 on 2, then inverse exists. G to G is also 1 1 and on to. Okay. 1 1 on to. Now, but F inverse is 1 1 on 2. Till now we have not shown that this is a homomorphism. Okay. Now we will show. Okay. Let A and B belongs to G. Okay. Then there exists A dash and B dash belongs to G such that A is equal to F A dash, okay, and B is equal to F B dash, okay. Why this is happening? Because F is surjective. Sorry, because F is on to. F is on to. So F is on to, that is why this is happening. Okay. Now, so F inverse AB. F inverse AB, how we can write it? Okay. Okay. So F inverse AB. So now what is AB? AB is equal to F A dash F B dash. Okay. So this is equal to, by property of homomorphism, we have A dash, okay, A dash B dash, okay. So from here, what we conclude? Because function is 1 1. So this implies we have AB is equal to F dash A dash F dash F A B dash A dash B dash. So what does it mean? Because F is 1 1. So this implies what is F inverse AB? F inverse AB is equal to A dash B dash. Okay. Okay. But what we have, since A is equal to F A dash, so this implies what is A dash is. So what is this? So this implies, what this implies? A dash is equal to F inverse A. And what is B? B is F B dash. So this implies B dash is equal to F inverse B. Okay. So this is up to this. Okay, now put this value here. What is A dash F inverse A? What is B dash F inverse B? So what we have? F inverse AB is equal to F inverse A, F inverse B. So this implies F inverse is homomorphism. F inverse is homomorphism. Since F inverse G to G is homomorphism, one and on to, okay, this we get F inverse belongs to AG. Okay. Next, what is F composed? What is F inverse? We have to show this is identity. Okay. We have to show that this is identity. What is this? This is F. Okay. What is this? This is F in, what is this? F inverse A, and we know that, I'm writing it directly. We know that you take composition of F with its inverse, that always gives you identity map. So F inverse is identity, and you take F inverse F, that is identity. Okay. So this implies F has its inverse in AG. Okay. Hence, therefore, inverse, therefore, inverse of an element in AG, therefore existence of inverse, therefore existence of inverse of an, therefore existence of an inverse, therefore existence of inverse of an element in AG follows. Okay. Hence, A is a group. Hence, AZ is a group with respect to composition of functions. Okay. Okay, today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you.